In natural settings, legged animals exhibit exceptional agility, characterized by dynamic movements, such as jumping. However, replicating these behaviors in quadrupedal robots presents significant challenges. When operating at high speeds, the robot's dynamics are impacted by several physical factors. Proposing a universal framework that enables agile and versatile jumping is significant for enhancing the mobility potential of quadruped robots. In this work, we introduce a novel training framework that achieves height-aware and omnidirectional jumping for quadrupedal robots. To facilitate the precise tracking of the user-specified jumping height, our pipeline concurrently trains an estimator that infers the robot and its end-effector states in an online fashion. In the low-level control loop, the estimated height is used to select the lowest point that the robot's center of mass can reach after landing. A state machine switch will occur at that lowest point from the jumping controller to the standing controller. Then the state machine can be changed back to the jumping controller according to the user input. With this mechanism on, the single jump can be realized. Without it, the robot will jump continuously. Our universal DeepRL jumping framework can realize omnidirectional jumping on quadruped robots. Multiple real-world experiments are conducted, including forward jump, backward jump, and side jump. The experiments show that our method allows the robot to successfully acquire versatile jumping skills. Our framework can also teach the robot to jump at two different heights according to the height command. Several experiments with the combined command inputs of two directions were conducted. In these experiments, the robot is required to track the commands in both X and Y directions or even the yaw command to control its orientation. The experiment results demonstrate that the robot is capable of simultaneously tracking the compound directional commands. We also conducted experiments on rotation jumping. The robot can control its body orientation and jump to different yaw angles. Besides, a novel reward is involved by solving the analytical inverse kinematics with predefined end-effector positions. Guided by this term, the robot is empowered to regulate its gestures during the aerial phase. To test the robot's gesture adjusting ability, we design a small frame traversing experiment. We also explore our framework's potential in accommodating to different gaits. The walking jump experiments are conducted successfully. We evaluated the policy on a highly challenging task, which is 270-degree yaw-turning jump. The robot is able to finish this challenging task in a well-coordinated manner with proper torque and satisfying the joint angle limits. To further demonstrate our method's jumping versatility and landing stability, several experiments were conducted including jumping over hurdle and landing on rough or soft terrains. To realize the safe and stable landing, we designed a pre-landing reward to regulate the robot's gesture before landing, which helps to realize the robot's soft landing. In order to test and show the generalization ability of our framework, we also test our methods on the Unitree Alien Go, which has much larger mass and different motor properties and morphology compared to Go 2.